Good everyone, my name is Graphics. Today we want to study a problem in thermodynamics under the topic energy distribution in thermodynamic process. Now if you look at the top of the screen, you realize we have a question there. And the question goes like this. It says in a closed system, 0.25 kilogram of air initially at 1.034 bar with specific volume of 0.849 meter cube per kilogram is compressed reversibly according to the law PV to the power of 1.3 equals to C, the constant, until its pressure is 2.068 bar. The specific internal energy kilojoule per kilogram of the air is given by U equals to 1.58 PV, where P is in kilonewton per meter cube and V is in meter cube per kilogram. Determine the heat transfer and sketch the process on a PV diagram. Now, when you see a question like this, the first thing that you should do is to write out your parameters. Now, one of the first things given in the question, if you look at the top right corner of the screen, discover that what is a closed system and the mass given there is 0.25 kilogram. So the mass here given, the M is given to be what? 0.25 kilogram. That is the mass given, right? Now the next thing here that we have is the initial. You say initially at a pressure of 1.034 bar. So the initial pressure P1, the P1 is giving us 1.034 bar, right? So from here we have this. Now the next parameter given is the specific volume, which is given as the small v initially, and that is given as 0.849 meter cube per kilogram. Then the next one given, we have the law given as what? P to the power of V 1.3 is equals to what? The C constant. We call it the polytropic equation here. Right? So I'll put it in bracket. I have polytropic equation here. Right? Now, in the polytropic equation, what you see as the power here is called as the polytropic index and is given as what? N. So it means our N is what? 1.3. Now we move forward. The final pressure P2 from the question, if you look at that statement, it says that what? Until its pressure is, so the final pressure, the process here will be 2.068 bar. So P2 is 2.068 bar. Right? Now, if we move forward, it says the specific internal energy of air is given by, so we said the expression for the the internal energy specific is our small u is equals to what? 1.58 PV. So this is the expression given, right? I'll term it equation 1, right? So P is in kilonewton per meter square, and V is in meter cube per kilogram. So if you look at that statement, it says P is in kilonewton per meter square. So we need to convert all this pressure in bar into kilonewton per meter square. And how are we going to do that? Now look at this. We know very well that 1 bar is equals to what? 10 to the power 5 Pascal. So if I write it, that 1.034 bar is just as saying 1.034 times 10 to the power what? 5 Pascal. right? So it's the same thing as 1 bar. Now, if I use the law of my indices to split this up, I'm going to be having 1.034 times 10 to the power what 2 times 10 to the power what 3 Pascal, right? Now, if you look at this, your law of indices, when you have the same base, you add the power. So 2 plus 3 give me what? 5, right? So I can multiply 2 raised to the power 3, 2 raised to the power 2 is 100. 100 times 1.034 will give us 103, right? 0.4. Are you with me? Then this 10 to the power 3 means K. We have K P A. Is that taken? Now I said 10 to the power 3 means kilo. I is 1000. So I convert it to K. So this K represents my 10 to the power 3. Then this 10 to the power 2 is 100. I multiply with this. I'm having 103. I will know another Pascal, which is pressure, is measured in what? Newton per meter square, right? So I can also write this to be given as what? 103 kilo Newton per meter square. Is that taken? 103 kilonewton per meter square. That is 103.4 kilonewton per meter square. So either you write it this way or you say 103.4 kilonewton per meter square. The Pascal is force over area, and force is measured in Newton, and area is measured in what? Meter square. So let's move forward. Now, from here, this is the V1, the P2. I'll do the same process here. If I do the same process here, I will have in 206.8 kilonewton per meter square, right? I just apply the same process here and I have this. Now we've gotten P1, we've gotten P2, we've gotten V1, but we don't have V2. So what we'll do is we should calculating for specific volume, calculating for final specific volume, right? And that is giving us small v2 or v2. So from our polytropic equation, we say that recall P1 V1 is equals to what? P2 V2, right? So here we have 1.3, here we have 1.3. So recall from PV n equals to C. That's how we brought out this. Now we move forward. If I select, take all the pressure to one side of the equation sign, equal sign, and take the volume to one side, that means first of all, I'll divide both sides by P2, right? So I have P1 over what? P2. Sorry, say P2 here. Equals to, if I divide both sides by V1, I will have V2 1.3 over V1 the power of what? 1.3. This is what we have. So I took this down here and I took this down here. So we'll move forward. Now in your mathematics, recall that if I have A over B put to the power of n, it's going to give us A over B all to the power of what? N, right? So I'm applying it to this relation here. So here I'll have my P1 over what? P2 is equals to V2 over what? V1 all to the power of what? 1.3, right? Now, from here, I want to access V2, right? And I need to get rid of this 1.3. So if I'm doing that, what I'll do is, there's a relationship that says, recall, if I have A to the power of X equals to what? B, it's going to give me A is equals to what? Let me put it a to the power of x over y is equals to b. This will give me a equals to what? B to the power of what? Y over x. So when the power is crossing the other side of the equal sign, it changes position. The numerator becomes the denominator, the denominator becomes the numerator. So we're having this. So this is what I'll apply here. Now if you look at this guy here, is 1.3, but it's not standing alone. It is what? Over 1. So when it's coming to here, we'll be having P1 over what? P2. It's coming to the left hand side. So we'll have what? 1 over 1.3. So the 1 under comes on top, while the 1.3 on top comes under. This is just your indices here. So this is equals to V2 over what? Over V1. Now, if I make my V1, my V2 instead of the formula, that means I'm going to what? Cross multiply. So we'll now see that is V1 multiplied by what? P1 over what? P2, all is the power of what? We divide 1 over 1.3, we're going to be having 0.769 equals to what? Equals to V2. So this is what we're looking for. Now, what is your V1? V1 here is giving us, for what we've done in the beginning, V1 here is giving us what? 0.849. So we're going to input it there. We'll have our 0.849, right? Now, multiply by the P1 is giving us what we calculated earlier. P1 is giving us, we have 103.4. So we have 103.4. So when I put it here, the 103.4 all over P2 is giving us 206.8. 206.8 all to the power of 0.749. Now equals to what? V2. Now from here I can move further. This is like saying 0.849 multiplied by, we have 103.4 divided by 206.8, we'll be having 0.5, right? So this is 0.5. Goes to the power of what? 0.749. This is giving us our V2. So from what we have here, 0.5 to the power of 0.749, 0.749, right? So we're having 0.5950. So we're having 0.849 multiplied by 0.5950 equals to what? V2. So we can now say that the V2 here will now give us, multiply this times 0.849. So we're having 0.505. So the specific volume is giving us 0.5052 meter cube per watt kilogram, right? So that's our final volume, specific volume. So since we've gotten our specific volume, the next we calculate for is calculate for the equation. Say we should calculate for, look at the top corner of the screen. So we should look for what? The heat transfer, right? So we want to calculate for the heat transfer. So what I'm going to do here is this: calculating for heat transfer. That is the Q12, right? So what we'll do is you put recall. Remember that we know that the summation of the change in heat, the heat transfer, plus the work transfer, summation of the work transfer, is equals to what? Change in stored energy. But the stored energy we are dealing with is the internal energy. So I'll use U here, right? Now, from here, I can easily say that this will give me the Q12 plus the W12 is the process is equals to what? The change in internal energy. Now for me, if I make the Q12 the transfer to be the solution to the formula, I'm going to have the Q12 to be equals to change in U minus W12, right? So I'll call this my equation what? Equation 2. That taken? Now, for we to calculate the heat transfer, we need to know the internal energy, change in internal energy, and the work transfer. So the next thing I'll do is I'm going to be calculating for internal energy, right? So I call it delta U. That is changing what? Internal energy. So let's do that and see. Now recall, there's a relationship from the beginning of the question. Now parameter that we say that we call it equation 1. We have a relationship that says internal energy is equals to 1.58 pressure times volume, right? So recall from equation 1, that is in the parameters, right? From equation 1, we say that U is equals to what? 1.58 pressure times volume. Now, for state 1, right? For initial internal energy, right? For initial internal energy, that is U1, we're going to say that the U1 is equals to what? 1.58 P1 V1. Are we together? Now, we'll now see that the U1 here will now give us 1.58. The P1 given our question here is 103.4 times V1 is giving us what? We have 0.849, right? So when you multiply everything all together, the initial internal energy will give us, so we're having 138.7 kilojoule per kilogram, right? This is the initial internal energy. Now after we've done that, we're going to be calculating for the final internal energy. So calculating for final internal energy, right? That is U2. So we do that from equation 1. We say that, recall, just like we said earlier, U is equals to what? 1.58 PV. So therefore, my U2 will be equals to what? 1.58 P2 V2. So 1.58, the P2 here is giving us 206.8. We'll have 206.8 multiplied by the V2 is giving us 0.5052. So we multiply everything all together, we're going to be having this 165.07 kilojoule per kilogram. Is that okay? So we've gotten this. So therefore, the change in internal energy will now give us U2 minus what? U1, right? So this will now give us, what is the U2? 165.07 minus U1 138.7, right? So this is going to give us, this is going to give us, um, this will give us 29.37 kilojoule per kilogram. So this is my change in internal energy, delta U. Now we've done that. Now from our expression here that we calculated in earlier, we said that, recall, this we calculated for this already. Now we'll calculate for what? The work transfer. So our next target is to calculate for the work transfer. So I'm going to write it this way, calculating for work transfer. Now we're calculating for work transfer, right? So we note very well that the work transfer W12 is equals to what? P2 V2 minus P1 V1, all divided by the polytropic index minus 1. This is the formula for what? The work transfer. Now from here, now we put our value. We know that the P2 from our parameters is given as this. The P2 from a parameter is given as 206.8 times the V2 that calculated is given us as 0.5052, right? So minus the P1 is giving us 103.4, right? So multiply by the V1, that is multiply by the V1, which is given as 0.849, 0.849, all divided by the polytropic index, which is 1.3 minus 1. So from here, if you multiply all this, 206.8 times 0.5052, that gives us 104.48 minus 103.4 times 0.849. We have 87.78, capital C 0.79. This is what we have here. So all divided by 0.3, because 1.3 minus 1 is 0.3. So from here, this is going to give us minus 104.48. So we have 16.69. This gives me 16.69, right? So all divided by what? 0.3. So from what we have here, the work transfer W12 will give us 55.64, 55.64, right? Kilojoule per kilogram. That's the work transfer. So now recall, what you do is you now substitute W12 and change in internal energy into equation 2. Now the equation 2 we have here is giving us, the equation 2 we have given us Q12 is equal to delta U minus W12. So you see that Q12 is equal to what? Delta U minus what? W12. That is the equation 2. So we say that my delta U calculated was given us 29.37 minus W12 is given as what? 55.64. Look at the delta U that I calculated earlier here. This is our delta U here, 29.37. So move forward. So from here, if you subtract this, the Q12 will be giving us 29.37 minus 55.64. We have this. We have 26.27 kilojoule per what? Kilogram. Now value is in kilojoule per kilogram, right? This is our answer for what? Q12 in kilojoule per kilogram. Then in kilojoule, because it's in per unit mass, right? Which is your intensive property. Now to convert to extensive property here. Now recall. We know very well that the intensive property, right, is equal to what? The extensive property, right, all over what? Over mass, right? So since this is intensive, so for to put in extensive form, just in kilojoule, we cross multiply. Therefore, my extensive property, right, will now give me the intensive property times what? Times the mass. So let's put it this way. So from here now, if I now say that my Q12 in kilojoule per kilogram will be 26.27, right, times 26.27 kilojoule per kilogram, that is kilojoule over what? Kilogram, times the mass. What is our mass? The mass we calculated earlier was giving us 0.25 kilogram, right? So the kilogram here, we equate the kilogram here, we left with what? Kilojoule. So this will now give us from here 25.27 times 0.25. That will give us negative, because our value here is negative, right? Don't forget this is minus. We have minus 6.6 kilojoule. That's 6.6 kilojoule approximately, right? So if you found this video helpful, please don't forget to click on the subscribe button. Thanks for watching.